Hello, this is Jack Jackson. This video we're going to illustrate using GeoGebra. We're going to illustrate some of the basic postulates of these incidence postulates for Euclidean geometry. So just recall here's our list of our first postulates. And we're going to kind of go through these one by one and show how we can see them for Euclidean geometry. Now, first of all, postulate number one, the collection of all points in geometry forms a set called space. So for now, we can think of Euclidean geometry as being just 3 dimensions, even though a multidimensional Euclidean geometry is possible. However, a lot of what we will explore in this course will take place in a single plane. So let's start by just getting into GeoGebra. I'm just going to use it online. So if you go to GeoGebra, you get to this point right here. And then it may ask you to sign in. I've already signed in. I suggest you create in fact, for my class, you'll need to create a GeoGebra account. And I like to just use the GeoGebra Classic. So that's what we're going to do is go to GeoGebra Classic. And it starts with an algebra window and a graphing window by default. Now, for now, we don't really need these axes here. They're kind of there in the background because GeoGebra is kind of a connection between geometry and algebra, hence the name GeoGebra. So we don't really want these axes to show, so I'm just going to right click and tell it to not show the axis. So what's in this window right here represents a plane, or at least a portion of a plane. It goes on forever, up and down and left and right forever. Okay. So any location in here is a set of points. So we can use our point tool to create, say, a couple of points in that plane, and they can be moved around. Now, let me also show you something here. I'm going to also go here to View. I clicked on this little thing with the 3 lines for our menu on this side and go to View. And right now we're seeing the algebra view and a graphics view. We're also going to graphics and graphics 2 are 2 different 2-dimensional graphics views, but we also have a 3D graphics view that we can use as well. So I'm going to have that open as well. Now these points that I made here are actually in the XY plane. This is the XY plane here, which is this gray plane over here. So we can see those same points in both the 2D and 3D view. Okay, if I only want them to show up one place, so let's make another point here. I could take this particular point, for example, and right click on it and go to Settings, go to Advanced, and I could either show it in the graphics view and the 3D graphics view, and its coordinates show up over here in the algebra view as well. I can take it where it doesn't show up in the algebra view. Did you see it appear or disappear over there on the left? Or I could have it appear or disappear from the 3D view or the 2D view. So that's kind of useful if we want. Right now, let's keep them in both views. So this plane here is this gray plane here. Okay, so let's take a look at our situation. We have infinitely many points here and here, and so these are sets of points. We want to think of a point as being a location only. You see a dot there, which we can change to be larger or smaller, but in fact, that dot is just a representation of the point. The point itself has no size to it at all. It's just a location only. So that's an informal way that we want to think about points. Okay, so lines and planes are geometric figures. In fact, lines and planes are infinitely big sets of points in Euclidean geometry. There exist at least 4 distinct non-collinear, non-coplanar points. Okay, so let me show you how we can get a few of those. One way to do that, let's just kind of move these out of the way. Those are still in the XY plane. But I could put some specific points by typing in some coordinates here. So I'm going to start with the origin, where the 3 axes meet right here. That's the origin there. That's point D right now. And then let's go to point 1, 0, 0. There's 1. The point 0, 1, 0. That's 1 out on the y-axis. The first one was the origin. The second was 1 out on the x-axis in the positive direction. The next one's 1 out on the y. Let's go out 1 on the z. 0, 0, 1. Okay, and so those points D, E, F, and G are right there. That is a set of 4 points that is non-collinear and non-coplanar. So if we look over here, we can click here and rotate around. We can see that there's no line that will contain all 4 of those points, nor is there any plane that will contain all of them. I'm going to make some line segments with those as the endpoints. And this is going to make these line segments and these faces. If we connect all this together, these are the vertices and edges of a tetrahedron, a 4-phase polyhedron, also known as a triangular pyramid. Okay, so not a regular tetrahedron. This one has 4 faces that are isosceles right triangles, and this face that's slanted is actually an equilateral triangle. You can kind of see if you kind of look at it the right direction. Okay, so not all those planes, so some of those planes, 3 of them are, for example, in the XY plane, but the other one, 4th one's not. And there's no line that contains all 4, nor is there, or any 3 of them for that matter, and nor is there any plane that contains all 4. So there's many, many examples of that. That's just one out of infinitely many examples I could look at for that particular concept. Okay, every plane contains at least 3 non-collinear points. Okay, so if I want to use the tool to construct that, I can take 3 points that are not in the same plane, like these 3 here, and make a plane by going up here to the menu and saying plane through 3 points. And now I clicked on the 3 points. And this is going to be this slanted plane. Of course, if I complete the plane that contained the 3 down here, or all of these points over here, that is the gray plane there. And so now you can see the 2 planes. Of course, these planes go on forever. They're illustrated by these sort of parallelogram shapes here, but they in reality they go on forever in 2 dimensions and both directions there. Okay, let's see what else we can look at. Okay, postulate 5. Every line contains at least 2 points. And then postulate 6. Let's do postulate 6 first. Given any 2 distinct points, there exists at least 1 line that contains both of them. So I can create 2 points like I just did here in this plane here, the XY plane over here. And I can then take them and use the line tool to click on the 2 points. And it's using postulate 6 to say, okay, there's exactly 1 line that goes through those 2 points. So there is going to be an object there. There's at least 1 line, and there's at most 1 line as well. Shows that there's not going to be, there's no way to get another one. So this is a well-defined single object. Now notice it is dynamic in GeoGebra. So if I move one of the points, that line moves around. And right now, since I've had it turned on over here in this 3D window, you can see the same line right there being moved around as you move these points around the XY plane. Now, there are infinitely many points on a line. Okay, every line contains at least 2 points, which you have the line. There are points on it here. In fact, in Euclidean geometry, there are infinitely many points on the line. So I can take this, and if I take the point tool and click on there, or if I click on this point on the object and click the object, this creates some new points. So let me do a little color coding here. This one and this one. Let's go to settings, color, we'll make them red. So the 2 red points are the control points. If I move those are the ones that we started with in defining the line, that can move. But notice as it moves, these points were created not just as free points like this one, but as points on that line. So they're free to move up and down the line, but I can't move them off the line no matter how hard I try. And if I move the line, they move with the line. Now this point may be, temporarily it looks like it's on the line, but it's not constructed that way. As I move the line or move the point, I can move it off of the line. Very different than this one that's constructed on the line. You can do a similar thing here by constructing points in a plane. You can say point on object and click on this plane, and that point will stay in that plane. If I were to move the plane around, that would have to stay with that particular plane. Okay, so we're illustrating some of these basic concepts. Given any three distinct non-collinear points, there's exactly one plane containing them. Well, you saw me use that. That is how I got that blue plane a while ago. Okay. All right, postulate 8. If 2 points lie in a plane, then any line containing them lies in the plane. Okay, let's illustrate that in GeoGebra. So here we have a point in this plane. Here's another point in the plane. Okay, let's just make any 2 points in the plane. So a point on this object, another point on that, a line between these 2 points. So no matter where I move these 2 points, that line stays in that plane. Not just the 2 points, but the entire line that contains those 2 points. That whole thing stays in that plane. Okay, so we can see that illustrated. Next, it says if 2 distinct planes intersect, their intersection is a line. A good way to think of this one in the room is if you take the 2 walls that meet, they meet in a corner, which is a line going up and down. We can see that, whoops, let's go back. We can see that here by going to intersection of surfaces. I think that's right here. Yeah, intersect 2 surfaces. Click on the surface, that one, and then that one. And that gives us this line. It actually is in the XY plane, so it did show up over here. But you can see that the intersection there is a line. You see it as the blue line here, the blue line here. This is dynamic. Even though I put these with, by defining these points, I can move them around. So now there's the plane, but again, this point stays in that plane, and this point stays in the plane, and that line stays. This stays on the intersection, and so forth. Okay. So it gets us up to postulate 9, which is all the postulates we have thus far. So proposition 1 says there exist at least 6 distinct lines and 4 distinct planes. There are actually infinitely many points and lines and planes in geometry. In Euclidean geometry, you can kind of see that by just doing these manipulations. You can see, for example, as I move these 2 red points here, even in this one plane, I get infinitely many lines. And by moving this point up and down the line, I see there are infinitely many locations that point could be along the line. So in Euclidean geometry, we have a little stronger result. We're going to actually, at this point with our postulates, we're not guaranteed that we have infinitely many lines and infinitely many points, but that is true for Euclidean geometry, which does satisfy these postulates and propositions. If 2 lines intersect, they intersect in exactly 1 point. Let's see that illustrated. Okay, so I have 2 lines here. Let me hide some stuff, or actually just delete a few things. Okay, so here we have a line. Let's make another line. Okay, and then let's find the intersection of those two lines. So I can say intersect 2 curves, 2 lines in this case. And this point right here, let me give it a different color. Let's make it magenta or something. That point is the intersection of the 2 lines. So no matter how I manipulate them, there's only going to be one of those. It could be off screen, or there is a case where the lines are perfectly parallel and they don't intersect at all. That's okay for that particular proposition. It says if the two lines intersect, meaning they have a non-zero intersection, a non-empty intersection, then they intersect in exactly one point. Okay, and we can do the same thing in the 3D view. If we could make two lines here, we could intersect them as well. Okay. Proposition 5, if two lines intersect, their union lies in exactly one plane. Okay, so let's see that here. So here's a line. If I make just a free point here, let's see. Okay, and compare this line here and this point here. Well, if you take 2 points on this line and this is a point not on the line, those are going to be 3 non-collinear points. So you can do a plane through those 3 points like that. Okay. Different than our original one, perhaps, maybe. Okay. Let's give that that plane a different color. Okay. And so that pink plane is going to always contain this entire, not just these, not the 3 points I picked, but that entire line as well. Okay. Skew lines don't intersect. So what are skew lines? Skew lines are lines that there is no plane that contains all the points of all the 2 lines, and they would not intersect. In a room, that would be like the corner where the ceiling and the front wall meet. That's a line there, and then say a corner where the back wall and the side wall meet. That's a vertical line, and those 2 lines don't intersect. But there's no plane that contains all the points in those 2 lines. So those would be examples of skew lines. Parallel lines would be like where the front wall meets the ceiling and where the front wall meets the floor. Those might be parallel lines. Okay, so that gives you a little bit of a very quick introduction to some of the basic tools, just a few of the basic tools in GeoGebra, and see how they're related to our first incidence postulates.